In this video, we'll be looking at interior angles of polygons. So remember that a polygon is a straight-sided shape, and we talked about how it is a flat, two-dimensional figure with at least three sides and angles. So starting with triangles, if you add in another side, it just becomes a new type of polygon, but it is still a flat 2D shape that you could draw on a piece of paper. A diagonal in a polygon is a line segment that joins two of the non-adjacent vertices. So remember that a vertex is one of those points on the side of the shapes that connects the sides, and the non-adjacent vertices are the ones that are not touching each other already or right next to each other. So in a triangle, you have those three. Those are all adjacent because when I go to connect them, they have to touch one of the other ones that's next to them. Whereas in my quadrilateral, if I go to try to connect these and create a diagonal, I can't connect this left side because they're adjacent, but if I connect the bottom left with the top right, I've now created that diagonal with a non-adjacent vertex. And I can't do it from this point to the other one because that is adjacent to it. I could draw another diagonal here, which would create multiple diagonals in our quadrilateral, but that is as many as we can draw. So we're going to draw the diagonals in each of these shapes, but only from one vertex on each of these polygons to determine the number of triangles that are really hiding inside of each of these shapes. So in a triangle, if I start at one vertex, I can't connect it to another vertex without already being on a side. So there's only one triangle in a triangle. In our quadrilateral, if we start in this corner and we want to try to connect it to a non-adjacent vertex, we are going to go across the shape and we can create this diagonal. If I start in that same one and I go across the bottom, it's not creating any new triangles. So this quadrilateral is really broken up into two triangles. For our next shape with five sides, if I start in one corner, when I go to the first vertex, it's adjacent, so I can't create a diagonal. When I go to the next one, I'm creating one triangle. From that same original vertex, I'm going to the next one, which creates a new triangle. And to go to the last one, I'm on the bottom, which is not creating a new triangle. But you can see now that by these two diagonals that we've created, there are three triangles inside of this five-sided polygon. When we do it on our last shape, we cannot connect this vertex with this one because they are adjacent. We can connect it up to this vertex, over to the third one, over to the fourth, but we cannot connect it to the last one. So as you can see in this shape, we've now created four triangles. So what we're doing here is figuring out how many triangles are hidden in each of these shapes. Well, in the triangle, that three-sided figure, there were three sides and only one triangle. So the sum of the measures of those interior angles, that's something we've already studied this year, is our 180 degrees. Remember that a triangle always has that inside. Now our next shape has four sides, and that would be called a quadrilateral. In a quadrilateral, there are four sides, and inside of that, we created two triangles. The sum of the measures of the interior angles then in that in that quadrilateral would be 2 times 180 because there were two triangles inside. So what that really means is that we have 360 degrees inside of the entire quadrilateral. That is because we have angles in this first triangle, 1, 2, 3. These three yellow angles would add up to 180. And then these three blue angles would also add up to 180. And when you put them all together, they're creating the four interior angles of this quadrilateral, meaning we have a total of 360 in our quadrilaterals. In our five-sided figure, we call them pentagons. There are five sides, and we created 1, 2, 3 separate triangles. So that means that since there are three triangles and all of the interior angles of a triangle add up to 180, noticing these three separate angle measures in each triangle and adding them together would make all five of these interior angles of the pentagon. So that means that to get the interior angles of the pentagon, we would take 3 times 180 because there are three triangles, and that means there is a total of 540 degrees inside of a pentagon. For the hexagon, we can do the same thing. Our hexagon has 6 sides. We saw that there were 1, 2, 3, 4 triangles created. And because of that, same idea, there are 4 sets of 180 inside of this hexagon, making up all of these interior angles of the hexagon. So in order to get our sum of our interior angles of the hexagon, we will take 180 times 4 because there were 4 triangles inside of the hexagon. And that means that there is a total of 720 degrees inside of a hexagon. So that was how we could figure it out. If you had any size polygon with a given number of sides n, look at this pattern that we've now created. To go from 3 sides to 1 triangle, 4 sides to 2 triangles, 5 sides to 3, and 6 sides to 4, we are subtracting 2 each time. So the number of triangles that are actually inside of a polygon is represented here by n minus 2. Whatever the sides are, if you subtract 2, that's how many triangles can be created inside of it. So that means that if I wanted just a general formula to find the sum of those measures of interior angles, I would take 180 degrees times the number of triangles, which would be represented as n minus 2, because it would be however many sides minus 2 because of this pattern that we have seen. And that's how we could find the total sum of those measures. This is represented in our Polygon interior angles theorem that says the sum of the measures of interior angles in a convex n-gon would be represented as 180 degrees times the quantity n minus 2, where n is the number of sides. So in this case, we are just leaving it as a variable to represent that it could be any number of sides as long as it's greater than 3, because we talked about how polygons need to have at least 3 sides. So we're going to use this formula and apply it to some of these problems and figure out what the missing angles are in these examples. So in our first picture, we can see that there is a 4-sided figure, which means this is a quadrilateral. It has 4 sides, so our n in this case is 4. So we're going to apply it to our formula and write 180 degrees times n minus 2, but we're going to replace the n with 4. 4 minus 2 is 2, and we just have to multiply 180 times 2 for a total of 360 degrees. So that's the total sum of all 4 of these angles. Well, if they're all represented in variables or as numbers, we can now set up an equation knowing that if they're all supposed to add up to 360, we can take 2x plus 3x plus x plus 60 and set them all equal to their total of 360 for the quadrilateral. So you have 2 steps to do. Find out how many degrees are within your shape that you're looking at, and then create your equation. We'll combine all of our like terms, and we're left with 6x plus 60 equals 360. Subtract 60 from each side, and we're left with 6x equals 300. When we divide by 6, we are left with x equals 50. So that means that for our missing angles, we have 2 times 50, so 100 degrees, 3 times 50 for 150, and our last single angle of x as 50 degrees. If you added them all together, they should total to 360 degrees for a quadrilateral interior angle sum. In our pentagon, this time our n is worth 5, and so we're going to use our Polygon interior angles theorem of 180 times n minus 2 to get the interior angle sum. Our n is 5, 5 minus 2 is 3, so we are going to take 180 times 3 to get our total sum of our angles, which will be 540 degrees. Now that we know that all 5 of these angles are going to sum up to 540, we can use their expressions that are represented for their angles and create an equation by adding them all together. So we'll take 2x plus 4x plus 4x plus x plus 30 plus x plus 30. And all 5 of these angle expressions are going to sum up to 540 because of our Polygon interior angles theorem. We'll combine all of our like terms. We have 2x plus 4x plus 4x plus another x over here and here. We've got 12 x's plus 30 and 30, so plus 60, will equal 540. We'll subtract 60 from both sides, and we're left with 12x equals 480. And when we divide by 12 on each side, we'll be left with x equals 40. So that means that this angle up top would be 80 degrees. This would be 160, and so will this one. We add 40 over here, and these base angles are 70 degrees. So when we add them all together, they should add up to that total of 540. The last 3 problems that we have here say that given the sum of the measures of the interior angles, we want to classify the polygon by the number of sides. So this time, rather than knowing n, we know the sum that is going to be the interior angles. So we can still use the formula, we're just going to set it up a little differently. This time I'm going to write 180 times n minus 2, which is our formula, but I already know that the sum is going to be equal to 540, so I'm going to set that expression equal to 540 and solve for n. Since 180 is multiplying this entire group of n minus 2, we'll divide each side by 180. We're left with n minus 2 equals 3, and when we add 2 to each side, we can see that n would equal 5. That means that this would have been a pentagon, because n being the number of sides means we have a 5-sided polygon. In our next example, we will again set that expression 180 times n minus 2 equal to this new sum of 1,440 degrees. To get our groupings by itself, we're going to divide by 180 on each side. So we are left with n minus 2 equals 8, and then we'll add 2 to each side for n equals 10. That means that we have a decagon. There are 10 sides on that polygon. And last, we have a 2,160 degree interior angle sum of a polygon. So we'll take our expression to find the sum and set it equal to 2,160. Divide each side by 180, which leaves us with n minus 2 equals 12. We will add 2 to both sides, so n equals 14, which means we have a 14-gon figure. And there's no special name for that we're going to call it, so we'll just write it as a 14-gon.